Greetings to all, welcome to the channel Syntax 05. In previous few videos of the playlist Abaqus from Basic for Beginners, we discussed about the massing and modeling. So if you've not gone through those videos, I suggest to go through the videos if you are a beginner or if you are learning Abaqus. So here you can see part 1, part 2, part 3, part 4, part 5. In addition, I also explained the advanced massing and why we need massing, what are the element shape function and mass refinement, and then finally we talked about the finite element analysis and CAE, computer aided engineering. So after that we will start discussing new topic, that is part modeling in Abaqus. After the part modeling, we will go through the assembly, then we will go to the property, then we will switch to the step and so on. This is the Abaqus GUI. In previous video also we talked a little about this GUI. Here we have main menu, then toolbars and so on. In previous video we discussed. Okay, so to create a part you can go with the part modeling from the module, and here we have lots of options. Another thing, you can import your part from the any CAD software. Not all, but few CAD software file Abaqus accept directly, like from SolidWorks, CATIA. If you have any other software, then you can import the CAD file using the neutral file format. So to import the part, you have to right click on the part, then import. And here you have few formats like STA format, IGS, then step format. Those are the famously known format. Apart from, we have Parasolid and so on. If your part format is available in .inp, then also you can import that part. So let's cancel it, because right now we don't want to import any part. Instead of importing part, we will create a part in Abaqus GUI itself. So to create a part, you have to right click on the part options, or you can go with the manager, then click on create. The same definition you can access from here, but I always recommend to go through the manager, so you have list of features there, like you have 2 or 3 parts, so they will be listed down here. Now the biggest confusion will start. The confusion is we have lots of options here. So what is the modeling space, type, then options, base features, and then finally we have canvas size, or we can say the approximate size. So we will go through step by step. Let's first talk about the modeling space. Abaqus provides us 3 modeling space. As by name itself it clear, it is the space in which you want to model your part, whether your component is 3D part, whether your component is 2D, or it is axis-symmetric. So accordingly you have to choose. Let me show you some example in PPT. Okay. So in modeling space, whether you are in 3D or 2D planar or in axis-symmetric, these options, or we can say the type, is very common to everyone. Okay, like deformable, discrete rigid, analytical rigid, and Eulerian. Of course the Eulerian options not available here, we will talk on that later. But deformable and rigid, here also deformable and rigid, here also deformable and rigid. So let's start with the 3D part, 2D planar part, and axis symmetric part, then type, then we will move to the base feature. And lastly, approximate size, or we can say the canvas size, that is also common for everyone. Everyone means 3D part, 2D planar, and axis symmetric one. See, as I told you, the space in which you want to model your component is nothing but your modeling space. If you have complete 3D model, or you can say dimensions are quite comparable to each other, we have to utilize the 3D part. Here you can see the dog bone shape tension test specimen we have, and for that specimen I want to perform the damage analysis. So for that damage analysis, we model our component in 3 dimensions and perform analysis by holding from one end and applying load on another end. Similarly, here you have one plate. On that plate, you want to apply some bending load. So of course, those components are 3D component, and not only those examples, there are lots of examples of the 3D components. Even ideally, there is nothing like 2D and 1D. Everything is exist within the 3D. Even our smallest electron and proton having some volume, that's mean they are in 3D. But as an engineer, we always have to simplify the problem. Let's say we have one plate component that's thickness is very less as compared to the other dimensions. So we can see the figure here. And as we know, the thickness is very less, then theoretically that can consider as a plane stress component, because the developed stresses in the thickness directions are very negligible. So instead of modeling this component in 3D, we can model it into 2D. So what will happen? Our problem will be simplified. Simply here we may have 10 element along the thickness direction, and assume in the one layer we have 100 elements. So 100 into 10, 1000 element, and here only the 100 element will able to generate result with the same accuracy. So we simplified our problem. Okay, that's why we have to choose our modeling space very carefully. If we can utilize the 2D planar or axis symmetric options, then we have to apply. But there are few conditions like 2D planar. That's mean if you have plane stress or plane strain condition, then only utilize the 2D planar modeling space. In the 2D planar, you cannot model component in 3 dimensions. Here you have to model the component into 2D plane only. Okay. Similarly, the axis symmetric component. See here, this is our axis symmetric component, and the axis lie here. Let me create. This is my axis. Okay. If I revolve this plate, actually that's not plate right now. That's a simple rectangular section of the plate. If I revolve this section, this become a 3D plate. Okay, and for this 3D plate, of course, I can perform the analysis. Here it is forming analysis, but here you can see there are lots of elements, even thousands of elements, and in this plate we have only few hundreds of elements, and accuracy of result in the first case and third case is almost similar. So again, as an engineer, if we can simplify our problem, we have to simplify, and that's why we have axis symmetric options here. There are lots of restrictions to utilize the axis symmetric component, that not only the model but also the boundary conditions also symmetric. There must be an isotropic material and so on. So now we know very well about 3D modeling space, 2D modeling space, and axis symmetric modeling space. So now move to the next point, and that is type. Actually, we covered this modeling space, then type. So basically in type we have 3 types. You may think like here we have 4, but why I'm considering as 3? I will let you know. Because this rigid, analytical, and discrete rigid is nothing but rigid component only. Okay. The first we have deformable, these 2 we have rigid component, and lastly we have Eulerian component. So within this one figure itself, you are able to figure out deformable and discrete rigid component. Here this car model, of course this car model, this is our deformable component, and because we are not interested on the result of the walls, so we can consider this wall as a rigid component. You may think, sir, why we are going to consider this component, this wall, is rigid wall? Because it's a deformable. There is nothing rigid in the universe. But the perspective is matter. See, here, let me check on the laser point. Here, we are interested to find out the results on this vehicle, not on the wall. Of course, there will be damage in the wall, but we are not interested on the results on wall at all. So that's why, to reduce the complexity, again we can consider this component as a rigid component. So what will be the benefit of considering this component as a rigid component? See, this is our wall. Okay, this is our wall. Assume this is our wall. And when we go to mesh this, likewise in 3D, okay, in 3D likewise, there are thousands of elements. Okay, but as we know, we are not interested what result are developed here on the wall. Then why we have to invest time on the analyzing this wall? Instead, what we will do, of course, we need massing for this wall, because we have to establish the contact between wall and between car, or we can say between vehicle. So we need what? Massing. We need elements here. We need elements here. So elements are necessary, but we don't want to compute the results on the component. So what we will do, we make it a rigid component. Okay, we make it a rigid component. So this all element degree of freedom will be restricted on one point, and that point is called reference point. So you may think like here we have 10,000 element, or for sake of simplicity consider 1000 element, and each element having 3 degree of freedom. So the total degree of freedom will be say 1000 element, and then we cannot calculate according to the element, because each element having some number of nodes. So assume there we have 1000 nodes, okay, and each node having 3 degree of freedom. So we have here 3000 degree of freedom, and for these degree of freedom, software has to be perform calculations. So instead of this, what we will do, we will make it rigid, okay, and we will constrain the degree of freedom of the whole component at only one point. So here, this point having only 6 degree of freedom. So earlier we have 3000 degree of freedom, and now we have only 6 degree of freedom. So that's why if you are not interested on the results of few components, we can make them rigid. But there are lots of constraints. Okay, it's not mean like this part, this back end of the car, and they are not going to deform, and then we can consider them rigid. It's not work like that. Okay, there are lots of restrictions, and we have to follow them to apply rigid boundary conditions. So in other way, in other perspective, you can understand likewise this airplane going to be hit some wall of the building. People doing such simulations nowadays. Okay, so in previous case, see, the wall component was not important for us, so we considered that as a rigid component. But in this case, we cannot do that, because we are interested to see the results on these pillars of the building. So now we cannot consider those pillars as a rigid. Previously we considered this wall as a rigid. That's fine, because we are not interested. But here we are interested to find the results on the pillars of the building. So in this way we can say the perspective is matter. And here both plane and this wall, both are the deformable. Similarly, here we have forming analysis. In this forming analysis, there is one deformable plate, and then we have punch and die. And with the help of some pressure force, we are going to deform this plate into die cavity. So you may think, sir, not only the plate component, but punch and die are also quite deformable component. Of course, they are deformable. And if we are interested in the tool life, then we cannot consider them as a rigid component. But in this analysis, we focused only on the component, the plate component, how it will deform and what pattern exactly we will get, where will be the maximum stress zone, where will be the thinning zone, thickening zone, etc. So this is all about the deformable part and rigid part. Okay. And lastly, we have Eulerian part. Of course, in the rigid part, we have two types like discrete rigid and analytical rigid. By name itself, it is very clear. Let me erase everything. The analytical rigid means that is already calculated one. Okay, the component, the rigid component having some predefined shape, not the arbitrary shape. So that's analytical rigid. Like we can say half sphere, or we can say half circle, some cylindrical shape. This predefined shape, if you want to utilize as a rigid component, then you can use analytical rigid. If you have very arbitrary shape like this die component, okay, this die component, so you cannot utilize here analytical rigid. You have to utilize the discrete rigid options. Okay, so there are limitations. What is the benefit here? See, in the discrete rigid component, you have to mesh the component. No need to define the property, but you have to mesh the component. And here in the analytical rigid, neither mass is required nor material property is required. But again, in the analytical rigid component, you cannot apply the automatic contact definition. You have to define the surface to surface contact definition. These are the restrictions actually. Okay, so many times people not even utilize this analytical rigid, they utilize discrete rigid only. And lastly is Eulerian domain. The Eulerian domain is something in which material flow can take place. Of course, that is quite different topic, and I already discussed that in my few video lectures. So I will not discuss much in detail here. When we have large deformation and element deformation may use problematic for us, then what will we can do? We can simply utilize the Eulerian domain, so material flow can take place within the elements. Okay, so that is completely different. Here you can see this region, this bounded rectangle is nothing but your Eulerian domain, and here this wide region is representing sloshing of the water. Okay, so water is sloshing within the Eulerian domain. So lastly, the base feature. As we discussed previously, this 2D planar component, of course, by name itself it is clear, it is in the 2D plane. It is only for the plane stress and plane strain condition. We cannot make a 3D component here. Okay, so that's why the base features like extrusion and those revolution and sweep options are not available here. Similarly, in the axis symmetric options also, these base features and types are not available. Base features are available, but types are not available. Means extrusion, revolution, those things are not available here. Okay, here we have always one confusion. Like here in the 3D, we are in the 3D here. Okay, this is first for 3D, this is for 2D planar, and this is for axis symmetric. So here in this 3D, we have cell options, wire options, point options. In 2D planar also we have cell, wire and point options, and here also we have cell, wire and point options. So what is the difference? So let me explain the difference. Okay, here the cell, like if you want to extrude this rectangle, okay, this rectangle, not in solid, okay, if you want to extrude this rectangle in the cell, so it may be shaped likewise. Okay, let me show. Let's say part 3D cell, or I can say cell 3D. Go to the cell, and here you have planar options, extrusion options. Okay, let's say plane options, cell planar, and then here also we have planar cell. That is quite confusing. Okay, so cell planar, go to create, and this is my plate. That's all. This is cell 3D. Again, create one more component. Let's say cell, but now that time it is 2D. Go to the cell. Okay, I'm going to create a little bit longer. So now we have two components, cell 2D, then cell 3D. See, this cell 3D component, okay, that we created using the 3D options, then cell and planar options. So this cell 3D component can be bent along the planar direction. The plane of the cell is x and y. It can be bent, it can be stretched in plane direction, x direction, y direction, as well as out of plane direction, and the out of plane direction is z direction. Here you can apply load and this can be bent. Okay, this can be bent. So it's mean the 3D cell and planar. This is only the feature to create a surface in the plane, but it can be deformed in the 3D space because we are utilizing here 3D. So it can be deformed in the 3D space. But if you utilize this options 2D planar and cell, let's say this second feature 2D planar and cell, you can make deformation in this component along x direction, along y direction, but you cannot apply any load along z direction, or you cannot get any deformation along the along the z direction. That's the difference. Okay, similarly, if you have axis symmetric and deformable cell, what it's mean, see, whenever we use axis symmetric option, there will be always one axis, and if you utilize the cell feature, then this will be the final outcome. What it's mean, this cell feature will be revolved along this axis, and basically this become a solid cylinder. So this is not a cell even. It's look like cell, but not a cell feature. It's a solid because when you revolve it along this axis, this become a solid. So that is the difference. Similarly, if you utilize cell and extrusion options, just go to here. Let's say this plate, and this is not a plate actually, this is just rectangle, and we are going to extrude. So this type of feature you can create in the 3D space, but in 2D space we don't have such options. So that's why this cell, planar options and extrusion options, and those all options are available, but those same options are not available in 2D plane and axis symmetric. Similarly, whatever the wire feature we have, that wire feature is planar, but that can be bent in any of the direction of the 3D modeling space. But if you go with the wire feature here, planar wire, that can be deformed only the plane. And the axis symmetric wire, that's mean is nothing but, yes please, just try to think about that. If this is the wire and this is the center of axis, and if I rotate this wire along the center of axis, this become a, of course, a cylinder, but a surface form. So now this is the surface feature. It's look like line, but it's a surface feature. And finally, see, when we go with the manager, we have definition of those. Say axis symmetric deformation model. These two are axis symmetric, these two are 3D deformable, and this is the 2D deformable. Okay, what we are talking about? Yeah, 2D deformable and wire feature. Here we have approximate canvas size. This canvas size is nothing but size on which you want to define the sketch. Let's say 200 and go to the continue. Now this size, this grid size is nothing but your 200 into 200. Let's say -100, 100. This will be the first point. This one will be the first point, and this point will be 100, -100. So -100 to here, from -100 to 100, that's mean 200 size. So if you want to change the grid size, let's say by default you choose the grid size 200, but you want to choose the 500. So you can go with this options, sketcher options. Then you have here grid options, auto. Instead of auto, just define this value, click on apply. So the grid size will be changed. Similarly, this gridding size also you can change. Say here we have grid spacing of 5 and you want to make 10, just 10 and apply, or you may want to define 20, apply likewise. Now click on OK. Not only this, here you have dimension options, what dimension precision you want to use, up to what decimal value you want to define the parameters. Let's say it is 2. Go to the dimension 200. So this will be, I need to change it, 200.005. Okay. So it will showing 200 only. Of course, it's a 200.005, but it is showing only 200. So just go to the sketcher options and decimal place up to 4, go to the apply. Now we have 200.005, go to the OK. So here we have these features, axis symmetric deformable, then 3D deformable and 2D deformable, but you cannot utilize these features together. If you have one part as a 3D deformable, you must have all parts 3D deformable in assembly. Let's say go to the assembly and just create this 3D cell. Okay, then OK. Now if you want to import the 2D cell, let's say 2D cell and click on OK. So it will show you the error because dimensions of these two parts are not matching. So you cannot do this. You have to utilize either 3D parts, either 2D parts, or axis symmetric parts only. So that's all for this video. Hope you are quite clear about the part modeling in the Abaqus and why there are lots of options available here. This is just to make our problem simplify. So thank you for listening. We will meet in next video that will be based on the part modeling features.